Alright folks, welcome back to the next lecture of FCI Physics for You. And today we're going to be talking once again about Newtonian mechanics, and we're going to be hitting question number 2 on the first concept inventory. But before we do that, we're going to introduce our sponsor, which is Brilliant. Without Brilliant, of course, we couldn't get any of our problems or our support. So yeah, that's really important to our mission of educating the world, and let's get started.
I need to practice.
What is that?
I really need to practice. Can you wait for your video?
And that's how you have to do it?
No, but I like doing it.
Stop.
Okay.
Just practice in your head. Alright folks, welcome back to the next episode of FCI Physics for You. Today we're talking about Newtonian mechanics, but before I get any further, let's talk more about our sponsor, Brilliant. Brilliant.org is our biggest sponsor and our best sponsor. Without them, we couldn't have any of our support, and they're the people who support our mission of educating the entire world. So if you want to support Barry Science Lab, if you want to support Brilliant, then go ahead, wait to the end of this video, click on the link brilliant.org/Barry Science Lab for a 20% discount on a premium subscription. Okay, so question number 2 on the first concept inventory. Okay, so you got two metal balls and they're rolling off a table with the same speed. So if you're a high school student, you're probably tired of these questions. If you're not a high school student, you love these questions because this is what you see in real life. You have two balls and they're rolling off a table. So think about that. Which one is going to hit the ground first? Well, let me draw it out for you first. So we got a table right here and we got two balls. And remember, one of the balls has twice the mass as the other one, but they're both the same size. So you let them off the table, and which one's going to hit the ground first? Well, from the previous problem, we determined that both balls hit the ground at the same time, which is totally counterintuitive to your intuition. So that's really we have Galileo to thank for that. But this question is asking something different. If both of the balls have the same speed, which one will land farther from the table? Okay, which one? So let's do the math. But before we do the math, can we kind of predict? Can we predict which ball is gonna land farther from the table? Well, first things first, what are the givens? We have our two balls. They're launching from the same height. Let's call this height, let's call this H or D or whatever you want. There's only going to be one force when they leave the table that's acting on them, and that's the force of gravity. And finally, they're both moving at the same velocity. Of v meters per second. So my ball of mass 2m is moving at v. My ball of mass m is also moving at v. Question is, which one lands farther from the table? So once again, my prediction, without doing any of the math, is that both of the balls land the same distance away from the table. And why is that? Why do I predict that? I have no idea if that's going to work out with the math, but I predict that the distance d from the table to the balls are going to be the same. And why do I predict that? Well, it's because I don't remember mass having any relationship with range, right? The mass of a ball doesn't affect how far it ranges. So let's do the math and prove it. So let's use dx is equal to vixt plus half axt squared. Now remember, there's no acceleration in the horizontal direction, right? A lot of kids make the mistake, oh, there's a force acting on the ball because it's moving. No, there's no man pushing the balls. They're just moving. It's like you turn your head and you see these balls moving. There's no finger pushing the balls. So there's no acceleration if there's no force. So this thing goes to 0. How about their initial velocity? Well, that's just v. So this thing is going to be v. Sure, let's put in the time. We know the time is going to be limited by however the vertical range is. and I'm going to have dx equaling this. So that's it. I mean, this is kind of weirdly simple, isn't it? The horizontal range just depends on your initial velocity and the time. And of course, remember, the time depends on the vertical range and your height. But this looks like a really simple equation, and we know from the previous problem, we know that this time doesn't depend on mass. We know that. We know that the time doesn't depend on mass. What does it depend on? It depends on height. It depends on initial velocity. It does not depend on mass. Okay, so super weird. But once again, both of these balls should land the same distance away from the table. Now, the previous video I promised for you that I would show you how to derive one of these kinematic equations. So let's go ahead and try that. So let's see. I'm going to try to derive this one. Dx is equal to vit plus half at squared. So how should we derive this? I actually have absolutely no idea, sad to say. So let's say we start with the acceleration function of some particle. We want to get the velocity function, and finally we want to get the, what is it called, the distance function, the position function. So let's say the acceleration is constant. Usually in one-dimensional kinematics, or whatever, in high school you'll probably be left with constant acceleration problems. So let's say this is equal to a naught. Okay, so if the acceleration function is a naught, how can we get the velocity function? Well, remember that velocity is just the integral of acceleration. So to get from acceleration to velocity, we just take the integral, right? That's the awesome thing about calculus. All you do, take the integral with respect to time. So what do you get? You're going to get the velocity function. So v of t is equal to at plus c. I mean, who cares about plus c? Nobody. So the velocity function is at. Okay, good. Have you seen that anywhere? Yes, you have. Vf equals vi plus at. When vi is 0, you have literally your first kinematic equation. So you're welcome and congratulations. But we have more. Take the integral of this one. Maybe I need more space, so I'm gonna let us lasso select that. So lasso select that, and we're gonna bring this over here, and we're gonna integrate this with respect to time. So the integral of velocity with respect to time, well, what's that gonna be? Well, that's gonna be the integral of at. So let's take at, take the integral of that with respect to time, and what are you gonna get? Well, you're gonna get what? You're gonna get a times t squared over 2, which is just half at squared, right? Half a t squared.
Sorry, testing.
So what is our position function? Our position function is simply x of t, or d of t, whatever, is equal to half at squared. And once again, this is exactly what we get if our initial velocity is 0, right? Remember, that's exactly the equation we get over here. vit plus half at squared. If your initial velocity is 0, as in the case of a body falling from rest, well, then you're just left with half at squared, and that's exactly what we got, half at squared. So yeah, that's pretty amazing. As you can see, you can derive the kinematic equations on the spot. So what answer did we leave with? Well, let's read the choices. The two metal balls of the previous problem roll off a horizontal table with the same speed. In this situation, both balls hit the floor at approximately the same horizontal distance from the base of the table, and that was our answer. All right, ladies and gentlemen, before you close this tab, remember, just wait until the end of the video. Wait for the Brilliant sponsorship, because remember, if you want to support Barry Science Lab, you just support Brilliant, basically. So just hit on that link, brilliant.org/BarryScienceLab, and that will give you a 20% off the premium subscription. So thanks for supporting us, and thank you for supporting Brilliant. We'll check you out next time.
Ambition plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.